So the first thing we saw is that Bioconductor has whole libraries and annotation packages which contain sequences, the full genomes for our model genomes, but also have tools to allow us to import our own genomes as FASTA, our reference genomes, and then manipulate these and write them back out. Okay, so the next thing we're going to do today is, I think, one of the core fundamental parts of Bioconductor. And without this library, I think Bioconductor really wouldn't have survived the high throughput sequencing transition. And for me personally, this is probably one of the most useful libraries in my own career, and one I used a hell of a lot. So this is our talk on genomic intervals. How do we handle genomic intervals in Bioconductor? So we saw that genomic intervals are stored as bed files, right? These are very simple files. Chromosome, right? What chromosome the feature is on, what the start position of the feature, and the end position of the feature. Okay, so we know something was happening at this particular chromosome in this particular region. We also saw we can associate things like score, name, strand to this. So in high throughput sequencing experiments and genomics in general, we make extensive use of genomic intervals, which is why this is also important. And we use it to do things like store simple annotation. This is the location of a gene. These are the exons in a gene. This is the transcriptional start site. This is an enhancer region, anything which can be defined as regions. And we may also do things like, once we have our BAM file, as we'll see next week, we call peaks. For ChIP-seq, we identify regions where we see more signal than expected. And then we have a region of interest at that point. And we might want to store that as bed files too. We also want to be able, with these bed files, not just to store them, write them, we need to be able to apply functions to them that allow us to assess the spatial relationship between genomic intervals. Okay, so is our transcriptional start site near a particular enhancer? What is the distance between them? The enrichment for this ChIP-seq, this peak we've called, this enriched region, is it inside one of these TSSs? Maybe it's regulating that gene, or is it distal and we're not sure what it's regulating? Okay, so we don't just want to be able to hold this information, we need to be able to manipulate it, right? So in Bioconductor, to handle genomic intervals, we have really two major packages. We have our track layer, which might be soon replaced by the BioCIO package. But right now, this is the package we use to import and export genomic intervals in and out of R. The really cool package, I think, essential package in Bioconductor, which allows us to handle these genomic intervals, is this Genomic Ranges package. So it should allow us not just to store these intervals in objects, it has, importantly, the functions, the methods, which we need to be able to really interrogate these intervals. This is within this interval. This interval is close to this interval. So first thing we need to do is get a hold of this really cool package. I think the way to do that would be BioC Manager install Genomic Ranges. Just running this line here. All right, we had it on the front page. Again, this is the Genomic Ranges package. If we ever need to install it, you can just write and copy and paste this from the package page, copy and paste that into your R session, and then you're good to go. It's going to go install it and get all the dependencies. Okay, once we have this, in order to load any package, we need to do library. We give it the name of the library, and then Genomic Ranges loads, and it brings along all the libraries it needs in order to be able to do its functionality. So the first thing we want to do is actually create a genomic ranges, right? So we've learned how to deal with how to create vectors, data frames, lists, DNA string objects yesterday. So now we need to be able to create these genomic ranges, and they have, just like data frames, they have their own constructor functions. In order to create genomic ranges, though, we're going to need a set of genomic intervals, genomic ranges. And first, we need to actually create intervals. Okay, so ranges from 1 to 10, from 11 to 12, from 10 to 1000. We want to be able to create intervals. Now to do those, we can use this package, iRanges. This got loaded with genomic ranges, so we don't need to worry about loading it ourselves. We just use this iRanges function in order to construct from start and end positions our new object and iRanges object. Okay, so we take the iRanges function, and I'm going to give it my start positions for my intervals. My first interval will start at 1, my second will start at 10, my third will start at 20, and then the appropriate end positions. This is going to go from 1 to 2, the second interval 10 to 11, third interval 20 to 30. Okay. As usual, we can do the class, my intervals, and we can get the idea of what object it is. It is an iRanges from the iRanges package. Okay, when we look at this now, we can see it's taken this information and it's constructed our ranges. So if we just type into the console what our intervals are, my intervals, the object we've just created here, it will print out this, and it gives us a start, an end position, but it also gives us something new, which is a width column. Okay, so this wasn't created by us by creating start and end. It's filled this in. So that's how we just create standard intervals. And actually we use interval operations a lot in other things. We actually use it to build these courses. But in order to make use of it in genomics, we need to add just a little bit of information to this iRanges. We need to add additionally the chromosome and contig which this interval is on, right? We may know it goes from 1 and 2, but really being at this position on chromosome 1 is very different from being at that position on chromosome 2. So we can extend our iRanges by using a function, our first function from the Genomic Ranges package, this GRanges function. Okay, so this GRanges just takes our iRanges as our second argument, and for the first argument, it's going to take seq names and the names of our chromosomes matching our intervals. Okay, so our first interval is chromosome 1 and our third interval will be on chromosome 2. Now, if we get the class, we have something different. We have a GRanges, and this is from the Genomic Ranges package. So now we can look at our newly created intervals from the iRanges, and also adding our contig names. We have our my genomic intervals. It looks a little different now, right? It was a little bit more space like this, but it's the same information. We have strand, chromosome here with seq names. We have our ranges, the iRanges objects now nested here. And we have additionally something we haven't specified, strand information. Okay, so this by default has filled our strand in as star. And I said yesterday, a dot is means strandless. In GRanges, a star means strandless. So these have no strand. We can operate, even though these are a new object we have created, this GRanges object, we can actually operate them much like we can other bioconductor objects. If we wanted to get just the second and the third index, second and third row, we can use standard vector indexing or same except for indexing matrices or data frames. We just specify we want row 2 and 3, put it before the comma, and that should pull out the rows. An interesting difference of genomic ranges from vectors, matrices, and data frames is that in data frames and matrices, if we put a comma here, we'll get rows, but if we don't put a comma here and we just specify some numbers 2 and 3, it will actually bring out columns. Okay. In this case, we don't need to specify the comma. We can say we just want the second and third, and it will know to pick out rows. Okay, and that's actually because we don't have really column information here. This is more like a vector. Don't have column information yet. So if we want to start to access the column kind of information, so if we want to access the seq names and ranges and strand, and we can't do it through this type of indexing, we need something else. And actually what we have is these special accessor functions to both retrieve but also set this information. Right? So if I want to extract the start positions from my GRanges, I just use the start function. I give it my GRanges, and it's going to give me the start positions as a numeric vector. Similarly, if I want the end, it's going to give me the end positions as a standard numeric vector. I can also use that usefully to set my start positions. So if I want to modify these positions, these positions here, I can just use now the start function and use it to assign new positions. Okay, just as we would assign into a data frame or a new vector, we just have to put start, give it the GRanges we want to operate on, and then we give it vector the same length, same number of rows as is in our object. And then once I've done that, I've got my updated start positions. GRanges, being a clever object though, is going to stop you doing strange things. In this case here, in our thing, we have from 1 to 2, 10 to 11, 20 to 30. If I try and make my start positions greater than my end positions, right? So if I try and put my end position will be 2 for my first range, but now I want to make my start 10, it's going to tell us that's just not valid, right? Error, invalid iRanges. The width cannot be negative, right? The start can't be past the input. So that's good. It's going to protect us from doing stupid things. If we want to get the names of the chromosomes out, we have to use something different again. Typically, we would use names on a vector, right? Here we use seq names, and we just give it our GRanges, and it gives us back not a character vector, but gives us back a slightly strange object, a factor RLE. So rather than giving us back, a factor, it's giving us back now a factor RLE. Right, so we know we had 2 chromosome 1s and then a chromosome 2. And we can see that represented here in this factor RLE. We have 2 chromosome 1s, and then we have chromosome 2. So these contig names are stored in this special object, and this isn't a bioconductor object, although I think this flavor is bioconductor, but this is a general thing, and it's called run length encoding. You'll typically call them RLE. And this just allows the computer, the program, to save space, right? If I had 1,000 chromosome 1s in a row, which you may have when it's ordered by genome, I'm going to save a lot of space by just writing 1,000 and then chromosome 1 here. Okay. So we can save a lot of space, and actually it's probably quicker for the computer to be able to deal with it than if we bothered writing out all the numbers one after the other. Okay. If, though, we're not really wanting to work with a factor RLE, and we want to convert this to something we recognize, we can do as.character on that RLE object, and it just turns it back into a character vector, which we would be more comfortable working with. As with start and end, we can update these contig names. So I might now decide, oh, these features are all on chromosome X, chromosome 10. Okay, I can update that just as I did with the start and the end. So here, if I do seq names rather than retrieve them, it's actually, I can set them, and I'm going to set them to be chromosome 2, and chromosome 1. So I'm just reversing them. Right, and now it's just flipped my factor RLE, and I had 2 chromosomes and 1 chromosome. As with all factors, though, as Matt showed you on our first days, factors aren't quite so straightforward. This is a factor RLE we're getting out. If we try and replace values within a factor with a new value which isn't in the levels, then it's going to give us an error. And actually, it says this exactly here. Levels of supplied seq names, and it probably says must match current levels in object. Okay, so this is exactly the same issue as we had with normal factors and data frames. We have only the levels chromosome 1 and chromosome 2. I try and add chromosome 3, and it gives me an issue. Okay. So actually, we need to update the levels first, just like we would have done with a factor in a data frame. So rather than use the levels function, we can use now the seq levels function. First off, we can just see the seq levels available to us, chromosome 1, chromosome 2. And if I want to update that to include new chromosomes, I do seq levels, I give it my G ranges, and I give it my 3 chromosomes I actually want to be in there. Now I have my 3 levels. And then with this, I can start to add in my chromosome 1, my chromosome 2, my chromosome 3. Now I have the ability to add in this 3rd new factor. Without doing this, I'm going to get this error, and you're going to see this a lot if you try and replace things in G ranges. So we can easily solve that the same way we solve it for normal factors. We just need to change levels to seq levels and update the actual levels in our factor object. Okay. So the other thing we had in our G ranges was this strand information. Okay. And that was set by default when we created our G ranges. We can't have a G ranges without some type of strand information, even if it's just this unknown star, right, the unstranded. So we have 3 options available to us here. We can either be positive, negative, or unstranded, right? And this really is going to be important because we may be interested in only things in the positive strand, which overlap things in the positive strand. We may only care about, it being on the negative strand in 2 sets of intervals. So it's important to get this, and we can accommodate for it. If we wanted to explicitly set our strand in our G ranges, we just need to add another argument, strand, and we can just give it our vector here. We're going to tell it the first one's plus, the second one's minus, and the 3rd one's star. Okay, now I have my genomic intervals, and I have a concept of strandness here with positive, negative, and star. Similarly, we can extract and set this information. We had seq names, we had start and end, but we also have the strand function. And we can use this to set strand information. So we can do strand, our ranges, and I can reset them now to be plus, plus, and negative, whereas they were plus, negative, star before. And then I can retrieve that information. Okay, just like I can retrieve seq names. So this strand information, as we see, is stored again in a factor RLE rather than store loads and loads of pluses, strings of characters, a long vector of characters. It just stores how many times the character is repeated in a row. Okay. No matter what we create, though, we cannot update the available levels within our strand. Okay, so we have no problem ever, even if we don't have any positive, even if we don't have any negative values within our created G ranges, when we go look at this strand information, it always has the level plus, negative, star. Right? So in contrast to when we did seq levels, it only showed us the number of the levels of what the chromosomes actually in our ranges. Here it knows what the options for strand will be, right? No matter what we put in, it's always going to only accept positive, negative, and star. Okay, so the final thing I think we want to add to our G ranges, well, final 2 things, but the final thing to make it really look like a bed6 file, right, is some type of name. Just like we have names for our vectors, we have named vectors, and we can use these to index our vectors. We want to be able to do this for our G ranges too. So to do that, we can just use this names argument, names function, names our G ranges, just like we set names for standard vectors. We give it the names and we want to assign as a character vector. Now we have our G ranges. We have our standard G range here with all our strand information, our ranges, our seq names, but now we have what look like row names, but they're actually just names of our regions. Okay, what's really nice is that we can then use our standard indexing by name to extract the region, the range which we were interested in. Here I just want to find the peak, which I named peak 2. Can do exactly like I would do to a standard vector, square brackets, put in the name, and I've got my GRanges. So we often want to, if we look at this, it's a very flat GRanges, right? We have very simple GRanges: chromosome, start end, strand, and name. But we don't have anything like score. We can't attach any additional information to this range. And we really might want to, for when we're doing our analysis, we might want to put a name of the nearest gene. We may want to put a score of how much signal we have. So we can add and attach additional data to our ranges, making use of what they call mcols. So these are their metadata columns, right? So to add additional metadata columns, we can just either, when we construct our GRanges, we can just provide additional columns. So here I'm going to give a score, and I'm going to say it's going to have these values. I'm going to add comment, and I'm going to add some comments on arbitrary QC. And then this will then be included as additional mcols, metadata columns, when we create our GRanges. So I create my ranges as standard. That's going to go there. Create the seq names, which is necessary. I add in the strand information. And then after that, these are all additional columns. Score, I'm going to add comment. I could call them whatever I wanted. And they will be available to me within my GRanges data frame. So if I wanted to, once I've attached this to my GRanges, actually, I'm just going to build this quickly because I think it might be easier just to show you what it actually looks like. So we can actually see this. So I first need to load library GRanges probably. So then we have my intervals. And then additionally, I am sharing my screen, right? Yep. Additionally, I have the very basics for a GRanges now here. I'll just close that. I have my genomic intervals, chromosome, range, strand. But once I don't think I'm going to show it in the slides, so I wanted to show it here. But then I specify here the additional score and comment column. And you can see now we have our GRanges, which we had before, but now rather than 0 metadata columns, I have these 2 metadata columns, which I've just added. If I wanted to, I can make up any type of arbitrary columns, and I will just attach them here. Oh, I got to put a comma. And I can really create GRanges with any type of information I want stored within these metadata columns. These are more free form and effectively a data frame attached to my GRanges. Okay, if I want to actually retrieve the information then from that score column, which I just created, or from the comment column, I can actually use the standard $ accessor, which I had available to me for data frames or lists, right? So I want to pull out the score column. I just give it my GRanges, $, and I tell it, give me the score column. If I want to get the comment column, again, just $, and name of the column. If I want to create or retrieve all the metadata columns from my GRanges in one go, I can use this function mcols, and then that will just give me back a data frame. Here, it's actually a capital D, capital F. This is a bioconductor version of a data frame, but much the same. We can operate it the same ways. Okay, so we just bring back just the metadata as a data frame using this mcols function. If, and it can be very useful, if I wanted to lose all the functionality of my GRanges and I want to go back to something like a data frame, I can convert my GRanges to a data frame very easily just by doing as.dataframe, give it my GRanges, and then it converts, separates out the columns. Seek names now here, start here, end here. It gives me the width column, even though we never put it in, creates it for us. And then any metadata columns, it also brings back. Okay. This can be very useful for when you want to write out your GRanges to a file. You might want to convert it to a data frame first, and then you can pass that to write.table or whatever. Oh, cool. Thanks, Matt. I think a really lovely, useful function here. Hang on. Hey, Siri, can you open IGV? Thanks. I think a really lovely feature about genomic ranges, which actually escaped my attention for some time, is actually we can create GRanges just from a string. Okay, so if I want to create a single GRange here, I can create it using chromosome 1, colon, the start position, the hyphen, and then the end position here. Okay, you may have noticed, if I just stop sharing my screen for a second, that's actually exactly the configuration we use in IGV2, right? So if I go to Actin Vita, you know, this is the same configuration as we see here: chromosome, start position, end position. So it's obviously a standard way of representing genomic ranges. If you want to, you can just pass that into the GRanges constructor, just this, and it's going to give you a GRanges back. This is actually especially useful for when people give you file CSV information. And it means if they've given you an identifier in that format like this, you can just take a column information, apply the GRanges function to it, and just create your entire genomic ranges from a string. Okay, so what we actually do in the BRC, it's quite common. We may give you not chromosome start minus end. We actually give you chromosome start end, all separated by this colon. So to get us into a situation, we can use that in GRanges. I'm just going to show you, for example, how we can replace this colon. Okay, so we're going to use here briefly the string package, and this is, I think, part of string R, or is at least used by string R, which I think Matt showed you previously. Give it this range, which is a little bit different with the last colon. And we're just going to use this function, which does exactly what it says in the tin. String replace last fixed. Okay, so it's going to replace the last time it sees the colon in this string with a hyphen. Okay, if we give it our string, it's just going to go in, it replaces this with this, and then we have something we can pass to the GRanges function. Another common format, which you may see, and just to show you how you can clean it up, as you may see, I think this comes out of Max. The peak caller gives you something like this. You may see my ID, so a custom ID, a peak number, the chromosome, the start, and the end. To do this, we just replace the last colon with a hyphen. And then we will use the opposite, right? Stringy replace fixed regex here, right? This is because I want to use a regular expression. And I'm just going to replace anything, any word before the first colon with nothing. So I'm just going to remove the ID. And now I have a range, which I can finally pass to my GRanges, and I can create a new range. So these whole last few slides is just to really demonstrate. I quite like this function to just rapidly create a range, right? I know I just want to create one by example. But beyond that, because people will typically, including ourselves, give you combinations of where the actual position of this feature is in a text file as chromosome colon start end, you can actually just very easily rejig these a little bit, replace the last colon, remove the first ID, and pass these in to create GRanges too. Okay, so that's like the first half of this talk done. How we can create GRanges, how we can manipulate these once we have them inside our GRanges object. But like I said at the beginning, this is only really half the battle. Why not just store all my G ranges in a data frame? Much easier for me to access. Sure, I'm limited by some things which protect me in G ranges, like I can't make my start past my beginning, my start past my end. I can't put in unknown strange strand information, but really there's no advantage over a data frame yet. But that really comes at this point, okay? Because it's not just an object, it is actually an object with a set of functions, methods that we can apply to it. And some of the most useful functions we're going to show now hopefully demonstrate the use of G ranges. Okay. So some of the functions, I'm going to refer back to this page because it's kind of nice. Some of the functions we'll cover now are just to shift, to move our G ranges along some coordinates, to resize our G ranges, right? So now I want it to be centered on the start, maybe make it smaller, maybe center on the middle and expand from there a certain size. And another really useful function is reduce. And if I have a set of ranges which are kind of overlapping, and I want to simplify them and just give me non-redundant, non-overlapping ranges, I can use this reduce function, and it's going to collapse my ranges into long, contiguous bits of sequence, bits of range here. So let's see this in action. First function we'll look at is shift. Obviously, we could go in, manually adjust our start and end positions, but that seems like we would make more mistakes. We can just use this shift function. So on my ranges here, this is my first genomic range. It goes from 1 to 2. If you now pass this to the shift function and I say shift by 10 base pairs, and just shift equals 10, it's going to move this to the right 10 base pairs. So 1 to 2 becomes 11 to 12. Cool. The resize function is also going to allow us, the resize function is going to allow us to do something slightly different. It's going to allow us to actually change the size of our region. So here, if I take our third region, which was 2 to 30, in chromosome 2, here I can say I want the width to be 20. And what it's done is fixed on the start position. It's now resized this from 2 to 21 so that the total width of this range is 20. Okay, it's focused it on the start and then it's gone up 20. Like we just saw, by default, resize is going to, I'm going to get rid of this bar here. Resize is going to adjust the width of the regions fixed from the start of the region. We can actually control this behavior by adjusting the parameter fix. By default, it's going to be fix equals start, but we could say fix equals end, fix equals center. So in this case, I'm going to do genomic intervals 3 again. It's the original interval here. But rather than using the default, which fix equals start, I will use fix equals end. Now we can see that rather than going from 2 to 21, it's going to go from the end 20 backwards, right? From 30 to 11, fixed on the end of the region. Often, I don't think we're going to go into much more reason, but often you're going to use fix equals center, fix equals center for things like peak calling, right? You call your peak and then you just want to focus on the center, the highest point in your peak. So resize equals center is something which is super useful too. A clever feature of resize, again, why we don't necessarily want to do this ourselves by doing start and end adjustments, is that resize is going to take into account this strand information. I said this was important earlier on, and it really is here. When we say fix equals start, it's going to take into account whether or not the gene was on the positive or the negative strand. Okay, so when I say fix equals start and the region was on the positive, it considers the start to be the leftmost side of the region. If I then set the strand now to be on the negative, and apply the same function on the same strand, on the same region, we're going to get the backwards, right? It's going to go from the end that way. Okay, so this is really useful for things like genes. When we want to resize the gene start positions around the start position to get a TSS, this is super useful. It can also trip you up a bit, right? You might not expect this behavior, that this strand information is going to change this. So be aware of this. And if you don't want to deal with it and it doesn't matter to you, you can just set your strand to be star, and it will always work from the left when you say star. A final function which is really useful, and we're going to use this a lot in ChIP-seq and ATAC-seq, is this reduce function. Okay, so the reduce function merges overlapping regions into a single contiguous genomic interval. So let's make some regions to show this in action. We're going to go make regions chromosome 1, chromosome 1, chromosome 2. Ranges such that they overlap. I'm going to put them all on the same strand here as well. Okay, so we have a region here where these overlap by one base pair. This goes to 1 to 2, and this goes to 2 to 11. So they overlap on 2. This is on a different chromosome, so it really shouldn't overlap. If I apply the reduce function to this, genomic intervals, it's going to create a contiguous bit of sequence for this first overlapping bit of ranges. So 1 to 2 and 2 to 11 should become 1 to 11. And that's exactly what it did, right? 1 to 11. Chromosome 2.1 remains untouched because it's genomic ranges. It's not intervals. It knows this is on a totally different config, and it knows not to reduce it. Again, the reduce function is going to take into account strand information. Okay, so the importance of setting your strand information correctly, you can see here. Okay, so here I'm going to set the strand information now that the second interval on my first chromosome will be negative. Now, if I try and reduce this, you'll find that it doesn't reduce. Okay, and then that's because they're on different strands, and by default, it's not going to reduce across different strands. Right? It's only going to reduce them if they're on the same strand or if they are star unknown. If we want to override that behavior, remember this isn't default, we can set ignore.strand equals true. And now it's just going to ignore any information we have here. It's going to still honor the chromosome information, but then it will condense this first region now into this long contiguous region. Okay, so then I think this function here is the reason why I came to GRanges. Because before you were allowed to do things like this over, you were really limited by how you may do this. That's a good question, actually. What does reduce do with metadata? So you can actually, sorry, Nathan, sorry, we had a question from Nathan. So you can actually set reduce to do some clever things with metadata, like maintain it and compress it onto rows. So you can imagine if you wanted to, when these two things get compressed together, what it will do is, you can set this, is it will try and put the information into, with a comma separated, into the same row. Okay, so it can maintain your metadata information. It's very cool. Yeah, so this is really, I think one of the coolest things about Genomic Ranges is that it extends these operations we had for vectors, like percent in percent, this in operator we had, to now an over operator, which allows us not just to say this range matches exactly between these two sets of intervals, but this range is overlapping. It lands somewhere overlapping this range. So this is like a really cool feature of Genomic Ranges, and obviously fundamental when we want to work with alignments and assign scores from one set of ranges to another. So the first thing we need to do in order to start to work with the G ranges is create 2 sets of G ranges. So we'll do just that. Create 1 set of ranges here and a second set of ranges here using our standard setup. All on chromosome 1. And if we look here, we got our 2 ranges. Chromosome 1, 1 to 20, chromosome 1, 25 to 30. And then here we have a range which is gonna overlap, right? This 22 to 27 should overlap with this 25 to 30. Okay. So if we want to find all the regions in genomic interval as 1, which overlap the intervals in genomic intervals 2, we can simply use this over operator as we have used the in operator before. Okay. So this is going to return a logical vector specifying if the regions in my genomic intervals 1 overlapped any regions in my genomic intervals 2. Okay, so we know we have the second region should overlap at least one of the regions in this set. And this is what we get here. False for the first one, true for the second one. There is no overlap for this region with any of the regions here. But this second region does overlap one of these regions. So we would keep that. So we can use then, in combination with what we learned about logical indexing for vectors, we can apply this my intervals overlap 1 over my my genomic intervals 2. And that's going to give us false and true. And we can use that to subset our genomic intervals to just bring out the intervals in this set, my genomic intervals 1, which had any type of overlap with this my genomic intervals 2. So you can imagine we may have our peaks, our transcription factor binding sites, and we just want to, they would be my genomic intervals 1. And we just want to subset them to those which have some overlap with TSSs. They could be my genomic intervals 2. This would allow you rapidly to do that. Okay, it doesn't matter. They don't need to be perfect matches. They just need to overlap in some portion. So a really useful function which extends this is find overlaps. So the find overlaps function works very much like the over function. We give it our first set of intervals here. We give it our second set of intervals here. And it's going to give us back a hits object. And actually it says hits object here, but it says sorted by query hits object here. This is actually in a very low level bioconductor package, S4 vectors. It's a very base level package. But what's really useful about this object is it contains not just that any overlap happened, it actually says the second range in this overlapped with the first range in this. It gives us effectively a data frame where we have where in our first ranges they matched with our second ranges. Okay, so now this is getting really useful. If I want to extract this hits here, or these subject hits, so which ones here overlapped from this range, or which ones overlapped from this range, I have to use either the query hits function or the subject hits function. So here it's going to do query hits, my overlaps, and it tells me 2. So that corresponds to this second range here. If I look in my subject hits, my overlaps is going to say 1, and then that corresponds to this one here. So then we can do, using our indexing again, here not with true or false, but with a number, right? This is 2, this is 1. I can then use that to index. I can get the regions here which overlapped. And in the same order, I can get the regions here which they overlapped with, right? So this region, we know overlapped with this region, and we can see that clearly. Another set of really useful functions for genomic ranges are these nearest, precede, and follows. Okay, so rather than worrying just about overlaps, we may actually worry about things like distances. What was the nearest? This enhancer region is nearest to this gene, so therefore this enhancer region may be having some regulatory action on that gene. Okay. So we can now use these functions. We create two sets of genomic intervals again. We can see them here. I've just made sure that this one is a little bit further away and that these two are after this one, but before this one. Okay, but these are our sets of genomic intervals. First thing I might want to do is just do this nearest function. So the nearest function accepts two sets of genomic ranges, just like we did for find overlaps. And it's going to compare these arguments, and it's going to give an index of the intervals in the second genomic ranges nearest to those in the first. Okay. Oh, the first nearest ranges. Okay, so it's telling us that here, for both our intervals, the nearest interval in the second was the first. Okay, nearest first, second intervals, and it's telling us in the second set, for both these intervals, it was this one, which was closer. And again, we can use that for indexing our genomic ranges, and I can give back in the order of the nearest ranges. Now the precede and follow work much in the same way as nearest, except as suggested in their name, they're actually going to look for things which are before or after some G ranges. So we can give the same setup for precede. We give it our G ranges of our first intervals and our second intervals. It's the same with follow. And then it's going to return the index of elements in our second genomic ranges argument that are preceded or followed by elements in our first genomic ranges argument. Okay, so let's see that in action. Here we're going to do genomic intervals 1, genomic intervals 2. And I want to know which ones they preceded, okay, which ones in here were preceded by these intervals. And it's going to tell me that these two intervals were preceded, had before them the intervals in genomic intervals 1. Okay, is that true? Yes. Both these intervals here precede this interval, right? But they're after this interval. Just like find overlaps was really useful if we want to know which region overlaps with exactly what other region in my second genomic intervals. We also have this distance to nearest function, and this accepts same arguments as nearest, same arguments as find overlaps, precede, follows, takes our two sets of genomic intervals, and it tells us which regions were the nearest. Okay, but it's also going to tell us the distance between these two intervals. Okay, so here I've taken my two genomic intervals, and it's telling me that this one here is closest to this first one here, and it's told me the distance between these is 7. Okay. Similarly, it's telling me the second hit in my genomic intervals first was closest to my first hit, my first range in my genomic intervals 2, and the distance was 17. So if we go back, we can look at that again. Here. Yeah, so I think this is the distance between here, and then here and here. But in both cases, this was closest to here, and this was closest to here, and then it gave me the distance between. Great. Again, if we might actually want to extract this directly, if we want to, we can use our mcols argument and use distances, and it will give us a data frame of these distances. This is what we're probably going to pass to ggplot to give us our distribution of distances between our two sets of peaks, regions, whatever. We could also just do dollar distances, dollar distance, and that would give us that too. Great. So we've shown a little bit how we can manipulate, create these G ranges inside R, right, by typing in our values. Fact is, really, we're not going to do that very often. We're going to have either created these values in a separate program. We're going to import annotation. There are lots of times where we may need to create regions, bed files outside of R and actually import these into R. Or we may do all our manipulations in R, find our overlaps, and we want to export that to visualize it in IGV. Okay, so the R track layer package, again, BioC.io package may replace this. This allows us to use both import.bed and export.bed to write and import GRanges to and from file. Okay, so we can load that and we can do my CysaPeaks. And I'm going to import.bed. Rather than say file equals, we say con for connection here. And then we're going to say the data, and it's going to read in this bed file. And you can see it does quite a nice job of reading in the standard bed. It gives us our seq names, gives us our ranges, strand, typically peaks are strandless, name and score columns. Right? Why it doesn't put name as an actual name, I'm unsure. But, you know, we can get this information into the GRanges. We can start manipulating very easily. If we want to write that out so that we can visualize this in IGV, we can use this in other programs. We can do export.bed, give it the peaks, and then just say more CysaPeaks.bed. So the connection we're going to write to this file. And now we can just take our GRanges and start to visualize it in IGV or use it in other tools. So now just to give us a taste of this interoperability between bioconductor packages, I wanted to show you how you can use a GRanges now to extract some sequences from our FASTA or our BS genome objects. Right? So we saw that we can load library, and we can load the whole genome for BS genome in a mouse UCSC MM10. And if I want to get the subsequence, I can use subseq. I can give it a chromosome. Right, this is a DNA string, so I'm extracting a chromosome as a DNA string. Tell it the start, I tell it the end position, and it's going to bring out the sequence from chromosome 1 to chromosome 100 within this DNA string, which was actually chromosome 10 of the MM10 genome. With GRanges objects, we can actually specify just that BS genome object, and we can provide a GRanges, and it's going to go and very quickly pull out the ranges underneath my peaks underneath my regions from the appropriate positions within our BS genome object. Okay. So my CysaPeaks is just, you know, the positions of where the peaks would be. And I can use this function getSeq, give it my BS genome object. Can be any DNA string set object, to be fair, so we can still use FASTA we read in. We provide the names, what we want to get, and we give it here our GRanges object, and it's going to give back something hopefully we recognize, a DNA string set object with every row here, just length 3, being the sequence under the relevant peak. So we can make our GRanges we've just read in our BS genome and start to extract information, sequences under the peaks, which we may want to then write out and use for further analysis. So we can just use write_x string set, these new sequences, this DNA string set we just created, and write it out to cysaseq.far. And then we have a FASTA file, all the sequences under our peaks, perfect for motif hunting. Okay, so I think that's the end of our session for today. Have, I think, half an hour's worth of exercises, and we can look at them towards the end, so around 10:20, no, 11:20. I will come back and have a look at these with you. So if you want to go and have a look at the exercises, they're here. You should just be able to install some packages, create a box plot, create a GRanges, and then, you know, take this, visualize this in IGV, create some plots over what overlaps particular regions. So if you want to have a look at that, the exercises are linked here. The actual answers are here. If you don't want to hang around, you just want to quickly do this and then head off. If you want to work through this, I'll be back at around 11:20, and we can quickly go through it before the break at 11:30. What do we have to do? Okay, first off, install the Genomic Ranges and R track layer package. First thing, as always, we just go Google Genomic Ranges or R track layer. Should pull up a page like this. Every bioconductor package has this install. It's never going to do any harm to try and copy, paste into your R session, and then that should be installed with all its dependencies. So here we're just going to install BioC Manager, require, and then install these two. Read in the file data mic peaks.xls and create a GRanges object, which includes values of fold enrichment and -log10 p-value. Okay, ignoring this line, this is for me and Matt when we were trying to just make sure this can all be compiled automatically. So we actually don't need the R-track layer package, but we're definitely going to need the GRanges package here because we want to create a GRanges object. So we will load that. You may, just to remind people, I'm going to share a bigger screen. Let's do my desktop. So, great. So one thing which is very important is to make sure you're in the right working directory. So you can set that here, session, set working directory, choose directory. And what we want to be is once you've downloaded this course, you come in here, you can select our course, and we need to be in this directory here. Okay, and that's because we have all the data we're going to load is in here. Okay, so open that. Let's put me in that directory, and then I should just be able to run these commands. I can load the libraries. I can read this data in. So this was our MIC peaks. If we look, we have, I think, a data frame, a chromosome start end, length, scores, various information. And then just going to pass that into a GRanges so I can get the chromosome, right? This is this column, because that's got the cur1, it's got all the seq names. I create my I ranges from the start and end columns. Okay. And then I add additional metadata columns here. So I'm going to set fold enrichment to be the fold enrichment column, and the -log10 p-value to be the x log10 p-value column. So that should give me my GRanges. Perfect. Create a box plot of fold enrichments in genomic intervals over every chromosome. Okay. So really, I just want to have this GRanges as a data frame. We know that that's what ggplot requires. There's probably versions of ggplot which go straight from GRanges, but for here, we're going to use the data frame. We can convert GRanges to a data frame to allow us to write out or use ggplot. Just use this as.data frame. Okay, so we can actually, I can go and look at this in action. Wrong R. So if I turn that into a data frame, it's basically the same as when we read it in, but we have now width information, which is novel, strand information. And we've renamed some of these columns. And I think the next thing we want to do then is I can then do a box plot. So I'm going to do ggplot, pass it in my data frame. I'm going to set the aesthetics with X being the seq names. This is going to be the chromosomes. The Y is going to be the fold enrichment. And I'm going to do color just to make it pretty. Maybe I would want to do fill, but we'll do color here by the chromosome name, G on box plot, and then the theme is just going to be our black white. And then we should get our fold enrichments over the chromosomes. Okay. So the next thing I think we wanted to do is, filter. Make sure I'm sharing my screen. Yeah, the next thing we want to do is filter them, create a GRanges object of genomic intervals on chromosome 1 with scores greater than 10 and p-values less than 0.01. It's kind of easy to do. We're going to take our GRanges. We can get our column informations by doing $. So here I'm going to actually use the FE column, fold enrichment column, just to give us values greater than 10, which ones are greater than 10, and had a minimum log 10 p-value greater than, and then I'm going to do minus log 10. So because I'm already on log 10 space here, 0.0. Okay, so that will filter down my G ranges by peaks which have a certain fold enrichment and a certain log fold p-value, log 10 p-value. Further to that, I'm going to use the seq names to subset just to those in chromosome 1, and then I can export that to a file, a bed file, then just using export.bed from the R track layer package, giving it my filtered G ranges and telling it I don't actually have to say connection, but I'm telling it the file to write to here. Read in a text file of gene positions containing contig, names the seq names column, genomics start and end. Okay. From the file data gene pos for igv.txt and export to bed genes.bed. So I think this is just a translation exercise here. So I should just be able to read that in. I'm curious what I meant when I say what this looked like. Okay. All right, yeah, gene ID, seq name, start, end, width, strand. Okay. So I'm going to write out here a G ranges. I'm going to make sure we maintain the strand information. And I'm going to add in some names. So if I run this, importantly, if I just run that bit, we had our G ranges here, right? But I had no name information. So I added that with my names and then my G ranges. And now we have every single gene position for NM10, whether it was on the positive, negative strand, the chromosome, and the actual name. So these names aren't particularly useful to us, but these are the entrees gene IDs, and they will be useful. They're hard for us to read, but they are very useful because they're a great ID to have as your central ID. And they're very well maintained. With this information, we can then write that to a file. And it should be here. We should be able to just view it quickly. Oops, it's going to be big. But we can see what's nice. So I'm just looking at this file now. Chromosome, start, end, gene name, score, strand. Okay. There was no score here, so it just got put in as 0, but we did get the gene name. Okay. So by including the names here, when we exported this, we actually got a bed6 file. So when we read that in IGV, the names will be attached. Create a G ranges of transcriptional start sites of every gene, 1B, BP exact. So this is just an exercise on resizing. We can use the resize, give it the positions. We're going to say fix at the start, right? So that's going to take into account the genes are on positive on the negative strand. And it's just going to give us 1 base pair at the start. Extend these G ranges then to be plus or minus 500 base pairs around transcriptional start sites. Okay, so this is kind of common. First, we resize to the very start, and then with that new resized TSS, we will then expand around it using fix equals center. So we'll expand around that as the center and give us a 1000 base pair region. Okay. And then I'll just look at this and we can look at the IGV. Create a bed file called filtered mic on TSS.bed of our mic peaks from question 4. So these were our filtered mic peaks here, which we wrote out. Which overlap these ranges we've just created. Okay, so we can do that. We take these filtered ranges we created up here, and we can use, for the first time, this wonderful overlap function. So we take those ranges, and we just keep those which overlapped somewhere, one of these TSS extended windows around the start of a gene. Okay, so let's see that in action in R. So we have our gene pos here. We just exported these as a bed. I want to resize these to be the start, to be 1. So if we look, we have negative here. So that means the start would be the end. And that's exactly what we got. We had a positive here, which would mean the start would be the beginning. And that's exactly what we got. Okay, when we have this one base pair range, GRanges is just going to give us a 1 value here. So then we want to make them wide so we can actually get a TSS window. Now we can see we're extending around these regions, right? We've gone down a certain amount and up a certain amount, 500 around here. And then we wanted to take our, do I have these? We wanted to take our MIC filtered GRanges and overlap these with these regions. So we've just got them here. These are our filtered peaks. So we want to know the peaks which overlapped TSSs. We can use that, and that will give us a false or true to tell us whether or not a peak was in a TSS. And then we can use that index to subset down to our peaks. Okay. With that, now we can export our new filtered peaks over TSS regions to a bed file using this export.bed again. Okay. And somewhere in IGV, we should be able to load that back into our data. I think I'll have to change genome dash first, so I'll come back to that bit. Well, that's the next bit, right? Import the bed file filtered on MIC and genes.bed into IGV on the MM10 genome. Okay, so now I need to download a signal p-value bigwig. I should probably have downloaded that from the ENCODE portal for replicate 1 of the experiment ONS ROERN, and capture an image of the bigwig signal over our bed files over IGF BP2. Okay, so at some point you would need to go and just Google that. So I went there, and then I have my ENCODE portal, which we showed you on yesterday, and really useful. Anytime you need some data for these things, you can go and just look inside here and start to pull out various bigwigs. Okay, so in this case, we have 2 replicates. I can see the replicate number here, and I asked us to go get the signal p-value bigwig from the ENCODE portal for replicate 1 for this particular ENCODE experiment. Okay, isogenic replicate 1, signal p-value, bang. Right. So then we'll download that. This is going to take a little bit longer, but once you had that, you can then visualize that in IGV. Perhaps it won't take too long. We can come back to that particular bit. But the important part of that question was just to know to go find it in the ENCODE portal. If you didn't want to Google it from scratch, you could have just come to ENCODE itself and then use their search here. And it would have only brought up 1 value. And you just needed to go and look in the files for the relevant bigwig, which we wanted. Okay. Import the data mix ch12 input summits.bed into GRanges. The 5th column and file represents summit height. Okay, so I can import that just using import.bed. Data, give it the path, and we'll get a GRanges back. Generate a density plot of summit heights for summits overlapping and not overlapping TSS regions. Okay. So here we're going to take our summits, and we're going to use the, say, those which overlap this TSS pos extension. And now we're going to use this function we should have seen on the first few days, if else, right? So every time it's true, it's going to put TSS there, and every time it's false, it will put or return not TSS. And we're going to assign that to a new column in our GRanges overlap. And then from that, we'll create a data frame like we did up here. We want to create a data frame from our GRanges, because then we can just pass it straight to ggplot. And we can make our ggplot of our summits, with X being score, fill being the overlap, whether it was in the TSS or not. And then we'll just give us a geom density. I'm going to set the alpha to be halfway transparent, and we can facet it. So give us split it by the seq names, and then just add in the theme.bw. I like this black-white theme. Okay, filter the summits. GRanges to the top 500 ranked by the GRanges score column. Okay, just an exercise in using my summits. This is a GRanges, but we can do anything we could do to a vector. So here we can just order it, and I'm going to order by the score column, the score metadata column. Decreasing equals true because I want to go from most highest score to least highest score. And here I'm just going to take the top 500. Okay, so I'm just going to run these a bit just to catch us up. So we have my summits. This is our GRanges. We have a score column, a name, a strand, a ranges, seq names. Ranges is just one here because it's a summit. We have our extended TSS positions. I can get the true false, like I just said, of those which overlap. And then I will do my if else to turn this true false. Really, every time we see true, we'll get TSS. Every time we see false, we'll get not TSS. And I'm going to assign that to a new column in my GRanges, which will now be overlap, not TSS or TSS. Then turn that into a data frame so I can start to do things in ggplot. And then with that, I'm going to set my X to be, oops, sorry. I'll set my X to be the score, right? That's what I want to make the density of. I'll do the fill to be the overlap. Okay, so I want a different density plot for whether you're a TSS or not. And I'm writing this facet wrap, means I'm going to split this across every single chromosome separately. So that should give me something like this. Now, if I want to order this, I have my summits. I can order by any of these columns, but here I'm going to order by the score column. Right, so highest scores at the top, and then I'm just going to extract the highest 500. Right. So we just have the top, those top 500 scores. What do I need to do next? Extend these top 500 summit GRanges to 50 base pairs around the center of the GRanges interval. Great. And extract the sequences under the peak and write them to file. Cool. So this is the last thing we did in our course. Quite straightforward, really. We just need to resize these peaks now. Okay, so they're only the summit, right? So we can't really do much with the center or the end. We're going to do the fix equals the start or the end. We'll do the fix as the center. So centered on these points, expand it 25 base pairs either way to give us a width of 50. Okay. And now we have these 50 base pair summits. I'll load in the BS genome for MM10. Right? So this is our BS genome for mouse MM10 build. And I will use that function we saw earlier on, getSeq. I'll apply that to my centered summits. I'll apply that to the BS genome and my centered summits. And it gives me my DNA string set. Fantastic. Actually, I probably want to assign some names to that, right? Before I wrote that out. So I don't do that for some reason, but I think I should. Centered summits, do I have names associated? Yeah, I do. So let's do $name. And now we got some names associated to them, and I can write that to file. And here I'm going to write it to a FASTA file. It should appear in my local directory. And we have a little bit of sequence associated to every peak, right? So we've gone in, extracted the sequence, and now we have our valid FASTA with the name ID there, and then the sequence underneath, our next name, the next info line, the sequence associated. Okay, so I think we're done there. I'm going to come back at 12:30 for our final run through. And sorry, our next session, our next run through session. And we'll have some exercises at the end of that too. Okay, so I'll see you then at 12.